Hi guys, tonight we're exploring one of the most fundamental shifts imaginable. What if the speed of light, that sacred constant in physics, suddenly started slowing down? At first imperceptibly, but gradually reshaping the entire universe around us. If you enjoy these physics-breaking sleep stories that challenge the laws of reality, hit that like button and subscribe for more. And drop a comment letting me know what time it is, where you are, and where you're listening from. It's wonderful connecting with science enthusiasts everywhere. Alright, let's begin. Imagine waking up tomorrow morning and discovering that something fundamental about our universe has begun to change. Not the weather, not the stock market, not even the orbit of planets, but something far more profound and invisible. The speed of light, that most sacred constant in physics, the very foundation upon which our understanding of reality rests, has begun to slow down. At first, nobody notices. The change is imperceptible, perhaps dropping from its standard 299,792,458 meters per second by merely 1 meter per second per day. Such a minuscule shift would be lost in the noise of our most sensitive instruments, dismissed as measurement error by the few scientists who might detect it. But what begins as an academic curiosity would soon reshape every aspect of existence on Earth and throughout the cosmos. The implications of a decelerating speed of light stretch far beyond the realm of theoretical physics, reaching into the very core of how matter and energy interact, how time flows, and how the fundamental forces that bind atoms together maintain their delicate balance. This isn't merely a story about numbers changing on laboratory instruments. It's about the unraveling of reality as we know it. The speed of light, designated by physicists with the letter c, isn't just the velocity at which photons travel through the vacuum of space. It represents something far more fundamental. The speed at which cause and effect propagate through the universe, the rate at which information itself can travel, and the binding constant in Einstein's most famous equation, E equals mc squared. When c begins to decrease, the entire framework of physics begins to shift like a house built on slowly sinking ground. Consider what happens in the first weeks of this cosmic deceleration. Across the globe, physicists at institutions like CERN in Switzerland, Fermilab in Illinois, and the National Institute of Standards and Technology in Colorado begin noticing anomalies in their most precise measurements. The atomic clocks that form the backbone of GPS satellite networks, accurate to within 1 second every 37 million years, start showing minute discrepancies. These clocks rely on the hyperfine transition of cesium atoms, which oscillate at exactly 9,192,631,770 times per second under normal conditions. As the speed of light decreases, these atomic processes begin to shift in ways that initially baffle researchers. The Global Positioning System, a network of 31 satellites orbiting Earth, at an altitude of 20,184 kilometers, depends on extraordinarily precise timing to function. Each satellite contains atomic clocks synchronized to within 40 nanoseconds of coordinated universal time. When the speed of light begins to slow, the electromagnetic signals traveling between satellites and ground receivers start taking incrementally longer to complete their journey. At first, this manifests as GPS coordinates becoming slightly less accurate, perhaps shifting by centimeters rather than the usual millimeter precision that enables everything from precision agriculture to autonomous vehicle navigation. Within the first month, as the speed of light continues its imperceptible decline, strange phenomena begin appearing in laboratories around the world. At the Large Hadron Collider, where protons race through a 27-kilometer tunnel at speeds approaching that of light itself, particle physicists notice that their carefully calibrated experiments are producing unexpected results. the energy required to accelerate particles to near-light speed begins to decrease, not because the particles are becoming lighter, but because the speed they're trying to approach is itself diminishing. This change cascades through the electromagnetic spectrum in ways that initially seem beneficial. Radio waves, microwaves, infrared radiation, visible light, ultraviolet rays, X-rays and gamma rays all travel at the speed of light, forming what we call the electromagnetic spectrum. As C decreases, these waves begin to behave differently. Radio telescopes like the Very Large Array in New Mexico, consisting of 27 dish antennas each 25 meters in diameter, start detecting signals from deep space that appear to be arriving with slightly different timing than predicted. Astronomers initially celebrate these anomalies, thinking they've discovered new cosmic phenomena. The Sun, our nearest star located 93 million miles away, becomes the first cosmic laboratory where the effects become undeniable. Light from the Sun's surface normally takes 8 minutes and 20 seconds to reach Earth. As the speed of light slows, this journey begins taking longer, though the change is so gradual that it takes sophisticated instruments to detect it. Solar observatories like the Solar Dynamics Observatory, which monitors our star with instruments capable of capturing images every 12 seconds, begin noticing that the Sun appears to be operating on a slightly delayed schedule. But the Sun's energy production itself becomes affected in ways that reveal the true scope of this cosmic change. Nuclear fusion in the Sun's core converts 600 million tons of hydrogen into 596 million tons of helium every second, with the missing 4 million tons transformed into pure energy according to Einstein's mass-energy equivalence. As the speed of light decreases, this conversion process becomes less efficient. The same amount of mass now produces less energy, causing the Sun's total energy output to gradually diminish. This solar dimming doesn't happen overnight. The Sun's core, where fusion occurs, operates at temperatures of 15 million degrees Celsius, under pressures 250 billion times greater than Earth's atmospheric pressure at sea level. Energy generated in this core takes between 100,000 and 1 million years to work its way to the surface through the Sun's dense interior. However, the immediate effect on the electromagnetic radiation leaving the Sun's surface begins within hours of the speed of light starting to slow. Earth's atmosphere becomes an unintended detector of these changes. The ionosphere, a layer of charged particles extending from about 80 to 600 kilometers above Earth's surface, interacts constantly with electromagnetic radiation from space. As the speed of light decreases, radio waves begin to behave differently as they bounce off this ionospheric mirror. Ham radio operators, who have spent decades understanding how radio waves propagate around the globe by reflecting off different atmospheric layers, begin reporting unusual propagation conditions that don't match any known atmospheric phenomena. The global positioning system's degradation accelerates as months pass. GPS receivers, which require signals from at least 4 satellites to calculate position through triangulation, begin providing increasingly inaccurate readings. Commercial aviation, which relies on GPS for navigation across oceanic routes where no ground-based navigation aids exist, starts experiencing navigation errors that force pilots to rely increasingly on older inertial navigation systems. Ships crossing the Pacific Ocean, a body of water covering 165 million square kilometers, find their GPS-guided autopilot systems gradually losing precision. Meanwhile, in physics laboratories worldwide, researchers begin to comprehend the magnitude of what's happening. The fine structure constant, a dimensionless number approximately equal to 1 divided by 137, which describes the strength of electromagnetic interactions, begins to shift. This constant depends directly on the speed of light, and as c decreases, the fine structure constant increases, strengthening electromagnetic forces throughout the universe. This strengthening has immediate consequences for atomic structure. Electrons in atoms begin to orbit slightly closer to their nuclei as the electromagnetic force holding them in place becomes stronger. The energy levels of these electrons shift, causing atoms to absorb and emit light at slightly different wavelengths. In chemistry laboratories, spectroscopic analysis, which identifies substances by the specific wavelengths of light they absorb or emit, begins producing confusing results as familiar elements display unfamiliar spectral signatures. The pharmaceutical industry feels this impact acutely. Drug manufacturing relies heavily on spectroscopic techniques to verify the purity and identity of chemical compounds. Aspirin, manufactured at a rate of 40,000 tons annually worldwide, must meet precise molecular specifications. As atomic energy levels shift due to the changing electromagnetic force, quality control systems based on infrared and ultraviolet spectroscopy begin flagging perfectly good medications as potentially contaminated or incorrectly formulated. In hospitals, magnetic resonance imaging machines, which use powerful magnetic fields up to 3 Tesla in strength, along with precisely tuned radio frequencies to image internal body structures, start producing distorted images. The hydrogen atoms in water molecules within human tissue respond to electromagnetic radiation at specific frequencies. As the speed of light changes, these resonance frequencies shift, requiring constant recalibration of medical equipment that was designed to operate with unchanging physical constants. The effects ripple through the telecommunications industry with increasing severity. Fiber optic cables, which carry light signals through glass fibers thinner than human hair across distances spanning continents, begin experiencing timing issues. The internet backbone relies on these cables to carry data at near light speed between continents. A typical transatlantic cable, such as the 6,800-kilometer Maria cable connecting Virginia to Spain, normally allows data to travel between North America and Europe in approximately 65 milliseconds. As the speed of light decreases, this latency increases, causing noticeable delays in international communications. High-frequency trading, where computers execute millions of stock transactions per second based on microsecond timing advantages, grinds to a halt as the fundamental speed limit of information transmission begins to change unpredictably. Trading firms that invested billions in laying the shortest possible fiber optic cables between financial centers find their carefully calculated timing advantages evaporating as light itself slows down. Satellite communications experience even more dramatic disruptions. Geostationary satellites orbiting at an altitude of 35,786 kilometers above the equator rely on precisely timed signal transmission to maintain their communication links with Earth. As electromagnetic waves take longer to make the 71,572 kilometer round trip to these satellites and back, satellite internet services begin experiencing increasing latency that affects everything from remote education programs in rural areas to emergency communication systems. The power grid faces unprecedented challenges as the changing speed of light affects the behavior of alternating current electricity. Power lines carrying electricity at 60 Hz in North America and 50 Hz in most other countries operate according to electromagnetic principles that assume a constant speed of light. As C decreases, the impedance characteristics of transmission lines begin to shift, causing power distribution systems to become less efficient and more prone to instabilities. Nuclear power plants, which generate about 10% of the world's electricity from 440 reactors globally, encounter particularly complex problems. These facilities rely on precise electromagnetic control systems to manage nuclear reactions that must be maintained within extremely narrow parameters. The control rods that regulate neutron flux in reactor cores are positioned using electromagnetic actuators calibrated for specific response times. As electromagnetic signals begin traveling more slowly, these safety systems experience delays that require complete recalibration. The Diablo Canyon nuclear power plant in California, for example, generates 2,240 megawatts of electricity using 2 pressurized water reactors. Its safety systems include thousands of sensors connected by electromagnetic communication networks that must respond to emergency conditions within seconds. As the speed of light decreases, these response times gradually increase, forcing plant operators to implement increasingly conservative safety margins that reduce power output. Solar panels, ironically, become more efficient as the speed of light slows. These photovoltaic devices convert electromagnetic radiation directly into electricity through the photoelectric effect, a quantum mechanical phenomenon that depends on the energy of individual photons. As the speed of light decreases while the frequency of solar radiation remains relatively constant, the energy of each photon increases according to Planck's equation E equals h times frequency. This means solar panels begin generating more electricity from the same amount of sunlight, providing one of the few technological benefits of the cosmic slowdown. However, this advantage proves temporary and is overshadowed by more serious consequences. The Earth's magnetic field, generated by electric currents in the planet's molten iron outer core, begins to interact differently with the solar wind as electromagnetic propagation speeds change. The magnetosphere, extending approximately 65,000 kilometers toward the Sun, and millions of kilometers away from it on the night side, serves as Earth's primary protection against charged particles streaming from the Sun at speeds of 300 to 800 kilometers per second. As the speed of light decreases, the electromagnetic interactions between the solar wind and Earth's magnetosphere become more complex. Aurora displays, normally confined to regions within approximately 23 degrees of the magnetic poles, begin appearing at lower latitudes as the changing electromagnetic environment alters how charged particles interact with the upper atmosphere. Cities like Seattle, at latitude 47 degrees north, begin experiencing aurora displays that haven't been visible there for centuries. The biological implications of a slowing speed of light emerge gradually but prove profound. Photosynthesis, the process by which plants convert carbon dioxide and water into glucose using sunlight, depends on precise electromagnetic interactions within chlorophyll molecules. As the speed of light changes, the energy levels of electrons in these complex organic molecules shift, affecting the efficiency of photosynthetic reactions. Agricultural yields begin to fluctuate unpredictably. Corn production, which averages about 1 billion tons globally per year, starts showing variations that don't correlate with weather patterns, soil conditions, or traditional growing factors. Farmers notice that crops seem to respond differently to sunlight, with some varieties becoming more productive while others struggle. The changes are subtle at first, perhaps a few percentage points in yield, but they compound over growing seasons. Forest ecosystems, which contain approximately 400 billion trees worldwide storing about 550 billion tons of carbon, begin experiencing stress as the fundamental processes of photosynthesis gradually shift. Trees that have evolved over millions of years to optimize their light harvesting systems for specific electromagnetic conditions find themselves in an environment where the rules are slowly changing. Ocean ecosystems face particular challenges. Phytoplankton, microscopic marine plants that produce approximately 50% of the world's oxygen while forming the base of marine food chains, rely on photosynthesis just like terrestrial plants. As the speed of light changes, these tiny organisms experience the same shifts in photosynthetic efficiency, but their short generation times mean they can potentially adapt more quickly than larger organisms. The global ocean contains about 1,350,000,000 cubic kilometers of water, with phytoplankton distributed throughout the upper 200 meters, where sufficient light penetrates for photosynthesis. Changes in phytoplankton productivity ripple through marine ecosystems, affecting everything from krill populations that feed baleen whales to fish stocks that support billions of people worldwide. Climate systems begin exhibiting unprecedented behavior as the fundamental electromagnetic processes driving weather patterns slowly change. The Earth receives approximately 1,361 watts per square meter of solar radiation at the top of the atmosphere, with about 30% reflected back to space and 70% absorbed by the atmosphere and surface. As the speed of light decreases and electromagnetic radiation behaves differently, these energy balance calculations begin to shift. Satellite temperature measurements, collected by instruments like the Advanced Microwave Sounding Unit aboard NOAA weather satellites, start showing temperature trends that don't match existing climate models. These instruments measure thermal radiation from Earth's atmosphere at specific microwave frequencies, but as electromagnetic propagation changes, the relationship between measured radiation and actual temperature becomes increasingly uncertain. Weather forecasting accuracy degrades as meteorological models fail to account for the changing electromagnetic environment. The European Centre for Medium-Range Weather Forecasts, widely considered the most accurate global weather model, begins producing forecasts that diverge increasingly from observed conditions. The model processes approximately 40 million observations daily from weather stations, radio sonders, aircraft, and satellites. But as electromagnetic measurements become less reliable, forecast skill diminishes. Hurricane prediction faces particular challenges. These massive storm systems, which can contain energy equivalent to multiple nuclear weapons, depend on precise measurements of atmospheric temperature and pressure gradients. Weather reconnaissance aircraft flying into hurricanes use Doppler radar operating at electromagnetic frequencies to map wind speeds and storm structure. As the speed of light changes, radar measurements become less accurate, making it harder to predict storm intensity and movement. The aviation industry confronts mounting difficulties as navigation and communication systems become unreliable. Commercial aircraft complete approximately 100,000 flights daily worldwide, with air traffic control systems managing this enormous volume through electromagnetic communication networks operating at specific radio frequencies. As the speed of light decreases, communication delays increase, forcing air traffic controllers to implement larger separation distances between aircraft to maintain safety margins. Modern aircraft like the Boeing 787 Dreamliner incorporate thousands of sensors connected through electromagnetic networks that monitor everything from engine performance to wing stress. These fly-by-wire systems depend on millisecond response times to maintain stability, especially during takeoff and landing. As electromagnetic signals propagate more slowly, flight control systems require extensive software modifications to accommodate the changing physical environment. International aviation faces additional complications as different countries' air traffic control systems become increasingly out of sync. The Global Navigation Satellite System, which includes GPS, GLONASS, Galileo, and Beidou, provides worldwide navigation coverage through a constellation of more than 100 satellites. As these systems experience different degrees of degradation due to the changing speed of light, international flight routes become harder to coordinate safely. Space exploration encounters unprecedented challenges as the fundamental assumptions underlying rocket science begin to shift. NASA's Deep Space Network, consisting of 3 complexes in California, Spain, and Australia, with dish antennas up to 70 meters in diameter, maintains communication with spacecraft throughout the solar system. As the speed of light decreases, communication delays to distant spacecraft gradually increase beyond planned parameters. The Voyager probes, now more than 20 billion kilometers from Earth, normally require radio signals about 22 hours to reach them at light speed. As C decreases, this communication delay grows longer, complicating efforts to maintain contact with humanity's most distant ambassadors. More critically, the precise navigation calculations required for interplanetary missions become unreliable as the speed at which course, correction, commands travel to spacecraft begins to vary. The International Space Station, orbiting at an altitude of approximately 408 kilometers and completing one orbit every 93 minutes, experiences communication blackouts as electromagnetic signals between ground stations and the station take unpredictably longer to propagate. Astronauts aboard the station notice that their communications with mission control centers in Houston, Munich, and Moscow begin experiencing delays that don't correspond to orbital geometry. Satellite constellations like Starlink, consisting of thousands of small satellites providing global internet coverage, face cascading failures as the precisely choreographed dance of electromagnetic signals between satellites becomes disrupted. These satellites maintain their network connections by passing data between neighboring satellites at light speed. But as that speed decreases and becomes less predictable, the network's reliability degrades rapidly. The financial implications of a slowing speed of light reach into every sector of the global economy. High-frequency trading, which accounts for approximately 50% of equity trading volume in the United States, depends entirely on microsecond advantages in information transmission. As electromagnetic signals slow down unpredictably, these trading strategies become impossible to execute reliably, causing extreme volatility in financial markets worldwide. Global supply chains, coordinated through sophisticated logistics networks that track millions of shipping containers, trucks, and aircraft in real time using GPS and satellite communications, begin experiencing coordination failures. Just-in-time manufacturing, which minimizes inventory costs by precisely timing component deliveries, becomes impossible to maintain as transportation tracking systems lose accuracy. The Port of Los Angeles, which handles approximately 9 million 20-foot equivalent container units annually, relies on automated systems that track container movements, using GPS coordinates accurate to within centimeters. As positioning accuracy degrades, the port's ability to efficiently manage container traffic decreases dramatically, creating bottlenecks that ripple through supply chains serving the entire western United States. Scientific research itself faces an existential crisis as the fundamental constants that underpin experimental physics begin to change. Particle accelerators around the world, from the Large Hadron Collider to smaller university facilities, find that their carefully calibrated experiments produce increasingly unreliable results as the speed of light continues its gradual decline. The definition of the meter, officially defined since 1983 as the distance light travels in a vacuum in 1,299,792,458th of a second, becomes problematic as the speed of light changes. The International Bureau of Weights and Measures faces the unprecedented challenge of redefining fundamental units of measurement in a universe where supposedly constant values are no longer constant. Atomic clocks, the most precise timekeeping devices ever created and accurate to within 1 second over billions of years, begin showing systematic errors as the electromagnetic transitions they measure shift due to the changing fine structure constant. The cesium fountain atomic clock at the National Institute of Standards and Technology in Boulder, Colorado, which serves as a primary time standard for the United States, requires constant recalibration as the hyperfine transition frequency of cesium atoms gradually changes. Medical technology faces widespread disruption as diagnostic and treatment equipment calibrated for specific electromagnetic properties begins malfunctioning. Magnetic resonance imaging machines in hospitals worldwide require daily recalibration as the electromagnetic resonance frequencies of hydrogen atoms in human tissue shift. Radiation therapy equipment used to treat cancer patients must be constantly adjusted to ensure that electromagnetic radiation doses remain within therapeutic ranges rather than becoming harmful. Linear accelerators used for cancer treatment, such as the Varian TrueBeam systems installed in thousands of hospitals globally, accelerate electrons to near light speed before converting them into X-rays for precisely targeted radiation therapy. As the speed of light changes, these machines require complex recalibration to maintain the exact energy levels needed for effective treatment, while avoiding damage to healthy tissue. The pharmaceutical industry's quality control systems, which rely heavily on spectroscopic analysis to verify drug purity and potency, experience widespread failures as molecular absorption and emissions spectra shift due to changing electromagnetic interactions. The Food and Drug Administration and equivalent regulatory agencies worldwide face the challenge of revalidating thousands of drugs as their spectroscopic fingerprints change. Manufacturing processes dependent on laser technology encounter significant difficulties. Industrial lasers used for cutting, welding, and precision machining operate by focusing electromagnetic energy at specific wavelengths and intensities. As the speed of light changes, the relationship between laser power and cutting effectiveness shifts, requiring manufacturers to constantly adjust their processes. The semiconductor industry, which produces the microchips powering everything from smartphones to supercomputers, relies on photolithography processes that use ultraviolet light to etch microscopic patterns onto silicon wafers. These processes require extraordinary precision, with features smaller than 10 nanometers common in advanced processors. As electromagnetic radiation behaves differently due to the changing speed of light, semiconductor manufacturing yields decrease and production costs increase dramatically. Global communications infrastructure faces systematic breakdown as the timing synchronization essential for modern networks becomes increasingly unreliable. The Internet's backbone consists of fiber optic cables carrying data as light pulses across continents and under oceans. These systems depend on precise timing protocols to ensure data packets arrive in the correct sequence and without corruption. Undersea cables like the transatlantic telephone cable system, which carries much of the Internet traffic between North America and Europe through 6 pairs of optical fibers, begin experiencing increasing error rates as light pulses take longer and less predictable amounts of time to traverse the 8,000-kilometer distance. Network protocols designed for specific propagation delays start failing as these delays become variable. Cellular telephone networks, which serve more than 7 billion mobile phone subscriptions worldwide, rely on precisely synchronized base stations that coordinate using GPS timing signals. As GPS accuracy degrades due to the changing speed of light, cellular networks experience increasing numbers of dropped calls and failed connections as base stations struggle to maintain synchronization. Emergency services face critical challenges as their communication systems become unreliable. 911 emergency call centers in the United States handle approximately 240 million calls annually, routing them to appropriate first responders based on caller location determined through GPS and cellular tower triangulation. As these positioning systems lose accuracy, emergency responders increasingly struggle to locate people in need of help. The Federal Aviation Administration's next-generation air transportation system, designed to replace radar-based air traffic control with GPS-based systems, becomes unreliable as satellite navigation accuracy degrades. This forces a return to older radar-based systems, but even these electromagnetic systems experience problems as radio wave propagation becomes less predictable. Radio astronomy, which has revealed much of our understanding about the universe by detecting electromagnetic radiation from cosmic sources, begins producing confusing observations. The Very Large Array in New Mexico, consisting of 27 radio telescopes each 25 meters in diameter, starts detecting signals from familiar celestial objects that appear to have different characteristics than previously observed. Pulsars, rapidly rotating neutron stars that emit beams of electromagnetic radiation, like cosmic lighthouses, serve as some of the most precise clocks in the universe. These stellar remnants can rotate hundreds of times per second, with timing accuracy rivaling atomic clocks. As the speed of light changes, the apparent timing of pulsar signals shifts, initially leading astronomers to believe they've discovered new physical phenomena before realizing that the speed of light itself is changing. The search for extraterrestrial intelligence faces new complications as radio telescopes around the world begin receiving signals from space that appear to have different propagation characteristics. The Arecibo Observatory in Puerto Rico, with its 305-meter dish, and the Green Bank Telescope in West Virginia, with its 100-meter fully steerable dish, detect signals from known cosmic radio sources that seem to be arriving at different times than expected. Climate monitoring satellites, which track everything from atmospheric temperature to ice sheet thickness, begin providing data that doesn't align with ground-based measurements. These spacecraft use various electromagnetic instruments to measure Earth's climate from space, but as the speed of light changes, the calibration between space-based and surface measurements becomes increasingly uncertain. The Global Precipitation Measurement Mission, a constellation of satellites that monitors rainfall worldwide, relies on microwave sensors to detect precipitation through clouds. As electromagnetic propagation changes, these measurements become less accurate, making it harder to track global weather patterns and predict droughts or floods that affect billions of people. Ocean monitoring systems face similar challenges. Satellite altimeters that measure sea level rise by bouncing radar signals off the ocean surface begin producing inconsistent readings as electromagnetic wave behavior changes. These measurements are critical for understanding climate change impacts, as global sea levels rise approximately 3.3 millimeters per year due to thermal expansion and ice sheet melting. The TOPEX/Poseidon and JASON series satellites, which have monitored global sea levels for decades with millimeter precision, begin showing systematic errors that complicate efforts to track climate change. Coastal communities worldwide that depend on accurate sea level predictions for flood protection and urban planning find themselves increasingly unable to prepare for rising waters. Agricultural monitoring from space becomes unreliable as satellites equipped with multispectral cameras struggle to accurately assess crop health and productivity. These systems analyze reflected sunlight at specific wavelengths to determine vegetation vigor, soil moisture, and crop maturity. As electromagnetic radiation behaves differently, farmers lose access to the precise agricultural intelligence they need to optimize irrigation, fertilization, and harvest timing. The European Space Agency's Sentinel-2 satellites, which provide detailed imagery of Earth's surface every 5 days, begin producing images with color and spectral characteristics that don't match ground conditions. Farmers who have invested in precision agriculture systems that use satellite data to guide planting and harvesting decisions find themselves reverting to traditional methods based on local observation and experience. Urban planning faces new challenges as GPS-guided surveying equipment becomes unreliable. Construction projects ranging from skyscrapers to bridges depend on millimeter-accurate positioning to ensure structural integrity. The Burj Khalifa in Dubai, standing 828 meters tall, required extraordinarily precise surveying to maintain vertical alignment during construction. Similar projects become increasingly difficult as positioning accuracy degrades. Transportation infrastructure suffers widespread disruption as navigation systems become unreliable. The interstate highway system in the United States, spanning approximately 77,000 kilometers, relies increasingly on GPS-guided traffic management systems that optimize traffic flow and provide real-time routing information. As navigation accuracy decreases, traffic congestion increases, and travel times become unpredictable. Autonomous vehicles, which several companies have invested billions of dollars developing, become essentially inoperable as their navigation and sensor systems fail to function reliably. These vehicles depend on centimeter-accurate GPS positioning combined with electromagnetic sensors, including radar, LiDAR, and cameras. As the speed of light changes, all of these systems experience degraded performance that makes autonomous driving unsafe. The shipping industry encounters severe difficulties as vessels crossing oceans lose reliable navigation capability. Container ships, some over 400 meters long and carrying more than 20,000 containers, depend on GPS for navigation across open oceans where no visual landmarks exist. The Ever Given, which blocked the Suez Canal in 2021, demonstrates how a single navigation error can disrupt global trade worth billions of dollars daily. Maritime shipping carries approximately 11 billion tons of cargo annually, representing about 90% of global trade by volume. As GPS reliability degrades, ships must rely increasingly on traditional navigation methods, including celestial navigation and dead reckoning, significantly increasing voyage times and the risk of accidents. The aviation industry faces mounting crises as both navigation and communication systems become unreliable. Commercial aviation, which carries over 4 billion passengers annually, depends entirely on electromagnetic systems for navigation, communication, and collision avoidance. The Federal Aviation Administration manages approximately 44,000 flights daily in United States airspace, using a complex network of radar systems, radio communications, and satellite navigation. Air traffic control systems struggle to maintain safe separation between aircraft, as communication delays increase unpredictably. Controllers must implement increasingly large separation distances between aircraft to account for unreliable communication timing, drastically reducing airport capacity and causing massive flight delays worldwide. International aviation coordination becomes nearly impossible as different countries' air traffic control systems experience varying degrees of degradation. The North Atlantic Organized Track System, which coordinates the routes of approximately 1,500 flights daily between North America and Europe, begins experiencing coordination failures that force airlines to implement much longer, less efficient routes. Weather radar systems used to detect dangerous atmospheric conditions become less reliable as electromagnetic wave behavior changes. Doppler radar, which measures wind speeds within storms by detecting the frequency shift of reflected radio waves, begins producing inconsistent readings that make it harder to identify dangerous weather phenomena like microbursts and wind shear that threaten aircraft safety. The space industry confronts existential challenges as launch operations become increasingly unreliable. Rocket launches depend on precise timing and navigation systems to achieve the exact velocities and trajectories needed to reach orbit. SpaceX's Falcon Heavy, capable of delivering 63,800 kilograms to low Earth orbit, requires split-second timing coordination between its 3 first-stage boosters and continuous communication with ground control throughout launch and landing operations. Satellite deployment becomes problematic as rockets struggle to deliver payloads to precise orbital positions. The commercial satellite industry, worth over $300 billion annually, depends on satellites being placed in exact orbits with extraordinary precision. Communication satellites in geostationary orbit must maintain their positions within a few kilometers of their assigned orbital slots to avoid interfering with neighboring satellites. The International Space Station faces increasing isolation as communication delays with ground control become longer and less predictable. Astronauts aboard the station depend on continuous communication with mission control centers for operational coordination, scientific experiment guidance, and emergency support. Extended communication blackouts could force mission planners to consider early crew return or even station abandonment. Interplanetary missions face catastrophic consequences as communication delays to spacecraft throughout the solar system become unpredictable. NASA's Perseverance rover on Mars, located approximately 250 million kilometers from Earth when the planets are at their furthest separation, normally experiences communication delays of about 22 minutes each way. As the speed of light decreases, these delays increase unpredictably, making real-time mission control impossible. The James Webb Space Telescope, positioned at the second Lagrange point, approximately 1.5 million kilometers from Earth, depends on continuous communication with ground control for pointing commands and scientific data transmission. Unpredictable communication delays threaten the mission's ability to conduct the precise, astronomical observations for which it was designed. Deep space missions face even greater challenges. The Parker Solar Probe, designed to study the Sun's corona by flying within 7 million kilometers of the solar surface, requires extremely precise navigation and communication to avoid destruction in the Sun's intense electromagnetic environment. Variable light speed delays make it impossible to provide timely course corrections or emergency commands. Theoretical physics grapples with the implications of a universe where the speed of light is no longer constant. Einstein's theory of special relativity, built on the foundation of light speed as an invariant constant, requires complete reformulation. The famous equation E=mc² becomes problematic when c is no longer constant, fundamentally altering our understanding of mass-energy equivalence. Quantum mechanics faces similar upheaval as the fundamental constants that govern atomic and subatomic behavior change. The uncertainty principle, which relates the precision with which certain pairs of properties can be simultaneously measured, depends on Planck's constant, which is defined in terms of the speed of light. As c changes, the quantum mechanical description of reality requires revision. Particle physics experiments designed to probe the fundamental nature of matter and energy produce increasingly incomprehensible results. The standard model of particle physics, which describes the electromagnetic, weak, and strong nuclear forces along with all known fundamental particles, assumes constant physical parameters. As these parameters change, the theory's predictions diverge from experimental observations. The concept of causality itself becomes questionable in a universe with variable light speed. If the speed at which cause and effect propagate through space changes unpredictably, the logical sequence of events becomes uncertain. Scientific methodology, based on reproducible experiments that yield consistent results under identical conditions, breaks down when the fundamental constants of nature are no longer constant. Cosmology faces a complete revolution as observations of distant galaxies become increasingly difficult to interpret. The expansion of the universe, measured through the redshift of light from distant galaxies, depends on understanding how electromagnetic radiation propagates across cosmic distances. As the speed of light changes astronomers struggle to distinguish between true cosmological effects and changes in light propagation speed. The cosmic microwave background, the afterglow of the Big Bang that provides our most detailed picture of the early universe, becomes harder to interpret as the electromagnetic radiation from which it consists behaves differently than expected. Satellites like the Planck spacecraft, which mapped this radiation with extraordinary precision, provided measurements that must be completely reanalyzed as the speed of light changes. Dark matter and dark energy, mysterious components that comprise approximately 95% of the universe, become even more enigmatic as our to detect their gravitational and electromagnetic effects changes. These phenomena are inferred primarily through their effects on electromagnetic radiation from distant galaxies and the cosmic microwave background. As light behavior changes, distinguishing between dark matter effects and light propagation changes becomes nearly impossible. The search for gravitational waves, ripples in spacetime detected by facilities like the Laser Interferometer, Gravitational Wave Observatory, faces unprecedented challenges. These detectors work by measuring minute changes in the time it takes laser light to travel down perpendicular arms several kilometers long. As the speed of light changes, the calibration of these extraordinarily sensitive instruments becomes problematic, potentially masking or mimicking the gravitational wave signals they're designed to detect. Fundamental research in physics essentially halts as scientists struggle to understand observations that no longer match established theory. The scientific method depends on the ability to isolate variables and study specific phenomena under controlled conditions. When fundamental constants like the speed of light become variables themselves, controlled experimentation becomes nearly impossible. Universities worldwide face the challenge of teaching physics when the fundamental principles no longer provide accurate descriptions of observed phenomena. Textbooks that took decades to develop must be completely rewritten. But without a clear understanding of how the new physics operates, educators struggle to provide coherent explanations of natural phenomena. The technological civilization that humanity has built over centuries begins to crumble as the electromagnetic foundation supporting everything from electric power grids to computer networks becomes unreliable. Modern society depends entirely on technologies that assume unchanging physical constants. As these constants change, technological systems fail in cascading sequences that prove impossible to prevent. Emergency preparedness systems designed for natural disasters prove inadequate for a crisis affecting the fundamental nature of physical reality. Government emergency management agencies plan for earthquakes, hurricanes, pandemics, and even electromagnetic pulse attacks. But no contingency plans exist for the failure of physics itself. International cooperation becomes essential as no single nation possesses the resources or expertise to address challenges affecting the fundamental nature of reality. The United Nations faces unprecedented demands for coordination as countries struggle with simultaneous failures of technology, communications, transportation, and energy systems. Yet within this cosmic catastrophe, humanity demonstrates remarkable resilience and adaptability. Engineers and scientists work tirelessly to develop new technologies that can function in an environment where the speed of light continues to decrease. Some discover that certain technologies actually become more efficient as electromagnetic forces strengthen due to the changing fine structure constant. Communities that have maintained knowledge of pre-electronic technologies find themselves uniquely valuable as society adapts to a world where electromagnetic systems are unreliable. Traditional navigation techniques using celestial observation, mechanical timekeeping, and dead reckoning become essential skills once again. The crisis forces humanity to confront fundamental questions about the nature of reality and our place in the universe. If the most basic constants of physics can change, what does that say about the stability and predictability of existence itself? The discovery that the speed of light can vary challenges not just scientific understanding, but philosophical assumptions about the nature of truth and knowledge. As the speed of light continues its relentless deceleration, humanity faces a future unlike anything in the species' history. The electromagnetic civilization we have built must be completely reimagined for a universe operating under different physical laws. The challenge is not merely technological but existential, requiring us to rebuild not just our machines and systems, but our entire understanding of the cosmos and our role within it. This scenario reveals how profoundly our technological civilization depends on the stability of physical constants we take for granted. The speed of light isn't just a number in physics textbooks. It's the fundamental parameter that determines how energy, matter, and information interact throughout the universe. When that foundation shifts, everything built upon it must be reconsidered and reconstructed. In facing such a cosmic challenge, humanity would be forced to rediscover skills and knowledge that modern technology has made seemingly obsolete, while simultaneously pushing the boundaries of scientific understanding in entirely new directions. The story of a slowing speed of light becomes ultimately a story of adaptation, resilience, and the eternal human drive to understand and master our environment, even when that environment operates according to rules we thought we understood but clearly do not. Word count 6,847.